Today I'd like to look at integrating powers of secant, and specifically even powers. Unlike tangent, it's going to matter whether that degree is even or odd. We'll have a different approach. So first, let's look at even. We know the very first even power, secant squared, from Calc 1, because remember, the derivative of tangent is secant squared. So this is simply tangent x plus a constant. So now let's look at what happens when you go to higher and higher even degrees. And I'll just skip up to 6th degree to make it a little bit clearer. But the idea is this is a repeated process. Every time you do it, you're going to lower the degree of the integral by 2 so that you eventually get down to an even degree. So let's start with, say, secant to the 6th. All right, and the idea is we're going to factor off a secant squared from that. So that becomes secant to the 4th secant squared. And the reason we're going to do that is we're headed towards a U-substitution. The idea is that this part right here will end up being our du. So u would be tangent, right? The derivative of tangent, secant squared. So now the goal is to write this secant to the 4th in terms of tangent. Well, the key to this being able to be done is that that is even degree, because we started with even, you take off 2 and you're still even. And because of that, you can write that as secant squared to a power, depending on what your original power was. This will only be 2 less, it'll still be even, and this number here will be half of that. And now, since you can rewrite this in terms of a power of secant squared, you can use the Pythagorean identity. Secant squared is 1 plus tangent squared. And now we're ready for U-substitution, because remember, this was going to be our du. Tangent then can be our u. So our u here is tangent x, du secant squared x dx. And now this whole thing can be rewritten 1 plus u squared squared du. Now, this is just a polynomial. Go ahead and FOIL that out. And now we can just integrate by power rule and return to our original variable. So the integral of 1 would be u, which is tangent. To u squared, the antiderivative there would be 2/3 u cubed. So 2/3 tangent cubed. And lastly, 1/5 u to the 5th, 1/5 tangent to the 5th, plus the constant. So if we look at what happened here, no matter what this degree was, could be any even number, 8, 10, 12, whatever. You take 2 off, you'll be left with something that's still even. And because it's even, you'll be able to write it as secant squared to some power. So what's going to change is right here. The higher that degree, the bigger that power on 1 plus u squared will be. This could be squared, cubed, 4th, 5th, 6th, as you go up higher and higher in that original power. So what happens is the higher that degree goes, the more algebra you're going to have there. What's really helpful is as that number gets bigger and bigger, if you remember your binomial theorem and Pascal's triangle, you can expand that out a lot quicker than trying to do all the multiplication. And so then we end up just integrating a polynomial every time. At the beginning, I said we would lower this 2 degrees at a time, but that was not the case here. I was thinking of odd degrees. Odd degrees will have that reducing 2 at a time. Here, we will get, no matter what that degree is, the only thing that changes is there's a little more algebra here. You get a bigger polynomial, but it's all done in the same amount of steps. So next time we'll look at the odd degrees of secant, which that will be a power reduction.